The information we calculate goes beyond mean, median, and mode. We also need to know about something called variation, which we'll talk about in this section. So let's look at an example. You can wait in line at two different banks. Each bank has 3 lines, and at Old Bank you have somebody who waited 1 minute, somebody who waited 3 minutes, and somebody who waited 14. Whereas at New Bank, there's one line that queues into 3 tellers, but the important part is that the people waited 4 minutes, 7 minutes, and 7 minutes. Now, at both of these banks, the average wait is 6 minutes, but that doesn't really give you a clear picture of what's going on, because at Old Bank you could pick a short line with a minute wait, but you could accidentally pick the one that has a 14-minute wait. Whereas at New Bank, they're closer together, 4, 7, or 7. So which one would you prefer? Most people would pick New Bank because even though none of the waits are as short as the 1-minute wait at Old Bank, it's a little more consistent, a little more predictable, and that's what variation can help us to figure out. How consistent are the values for this data set? When we're looking at how much the values vary from each other, there are 3 different types of variation that we can talk about: range, standard deviation, and variance. These are all very important. We're going to talk most about the first 2. And just to mention ahead of time, the rounding rules on these will be the same as mean and median, where you round 1 decimal place farther than the original values that you were working with. So the first kind of variation that we talk about is range. Range is a very easy thing to figure out. It's just the highest value minus the lowest value, but this only really gives a limited amount of information. If we look back at the bank example at Old Bank, the range is the 14-minute wait minus the 1-minute wait. So there's a 13-minute difference between the short wait and the long one. At New Bank, 7 minus 4 says that there's a 3-minute difference. So this gives you some sense that at New Bank there's not as much variation between the wait times, but it doesn't really tell you anything other than the shortest and the longest. It doesn't tell you how much variation there is in the middle. A very important kind of variation is something called standard deviation, and this will give us a little bit more information about what's going on with all of the values in the middle, not just the highest and the lowest. What it really tells you is the average distance that the values are from the mean. Most of the time we're going to be calculating this on our calculator because it's a pretty lengthy calculation by hand. Notation on this: for a sample, the symbol for standard deviation is just S, and then for a whole population, the symbol is the lowercase Greek sigma, so it looks like a little O with a tail on top. The standard deviation can be calculated really easily using the 1-var stats, which we talked about in the last section. So if you want to go back and watch that video again, when you pull up the 1-var stats screen, you've got the mean at the top, and then if you look down a little ways, there's an SX. That is your sample standard deviation, and if the numbers that you put in were actually the entire population, then your standard deviation is the sigma x right below it. Most of the time we are not dealing with the entire population, so when you do sample data, the calculation is slightly different to account for the fact that it's only a sample, and that will be the one that we're using most of the time. If you take a minute to calculate the standard deviation for each of those banks in your calculator, then you'll find that for the Old Bank the standard deviation is 7 minutes, and for New Bank the standard deviation is 1.7. So because New Bank has a smaller standard deviation, that's a more predictable wait time, and so that would be the one that we would prefer to be in. In general, smaller standard deviations are better from a statistical perspective, so keep that in mind. What this is really telling you overall is that at Old Bank, on average, the wait times tend to be about 7 minutes off from the mean, and at New Bank, the wait times on average are about 1.7 minutes from the average wait time. And just some things to think about with standard deviation: they would always have to be positive because we're talking about how far away values are from the mean. And if you have any extreme values, outliers that are way off from everything else, these can have a big effect on your standard deviation. So if you have some outlier values, they may make your standard deviation look much larger. When you're labeling standard deviations, it'll be the same label as the original values. So if you're talking about the minutes on the wait time, then your standard deviation would also be in minutes. By itself, a standard deviation is kind of hard to interpret. They're helpful for comparing two data sets, but if you're just looking at one data set, the range rule of thumb, or sometimes this is called Chebyshev's theorem, can be very helpful to help make sense of what that standard deviation is actually telling you. Range rule of thumb states that at least 75% of the data in your sample will be within 2 standard deviations from the mean. Sometimes that's 95%, we're going to talk about that later, but the 75% can go for all data sets. And so if you know the mean and the standard deviation, you take the mean minus 2 standard deviations and then plus 2 standard deviations, and this gives you an interval in which you would expect 75% of your data to fall. As an example of that, let's look at Newbank. We saw that Newbank had a mean wait time of 6 minutes and the standard deviation was 1.7. So let's look at what the range rule of thumb tells us about that. So with a 6-minute average, we can do 6 minutes plus 2 times the standard deviation, and then we can also do the mean of 6 minutes minus 2 times the standard deviation. And so we find out that we would expect 75% of the time your wait at Newbank is going to be between 2.6 and 9.4 minutes. It would be unusual to be outside of those values. Now the empirical rule lets us be a little bit more specific in particular cases where the data happen to have a symmetrical distribution. We talked about symmetrical and what that looked like. If your data happens to have close to a symmetrical distribution, we can be a little more specific and we can say that 68% of those values will fall between 1 standard deviation of the mean, 95% will fall within 2 standard deviations of the mean. That's going to be the one that we use the most often. And then if you go out 3 standard deviations, you'll actually catch about 99.7% of your data. So if we look at that visually, here's a bell-shaped symmetrical distribution, and the mean is right in the middle. And then this is showing that if you go out 1 standard deviation in each direction, x plus the standard deviation and then x bar minus the standard deviation, you catch 68% of your data, 34% in each direction. And then if you go out another standard deviation in each direction, you'll now have a total of 95%. That means if you do the subtraction, you've actually added 13.5% in each direction to get a total of 95%. And then if you go a third standard deviation out in each direction, you'll have a total of 99.7% of the data. And then I've done the math there to fill that chart in with the percentages that you've added in each direction would be 2.35%. And then that leaves 0.3% or 0.15% in each direction out on the ends. So the range rule of thumb and the empirical rule can give you some information about what the standard deviation is really telling you. Another thing that can be helpful is the coefficient of variation, which tells you what the standard deviation is as a percentage of the mean. So you take the standard deviation, divide it by the mean, that'll give you a decimal, and then you multiply by 100 to make that a percentage. So the coefficient of variation gives you a percentage. The coefficient of variation is helpful because if you have a standard deviation of, say, 100, you don't really know whether that's a big standard deviation or a small one. But if you compare it to the mean, if you have a standard deviation of 100 and the mean is only 10, then that's a huge standard deviation compared to the average value that you're looking at. But if your standard deviation is 100 and your mean value is 10,000, then that's not a very large deviation compared to the mean. So you can actually divide and figure out what percentage that is to tell you whether that standard deviation is very large in the situation that you're looking at. And then the last kind of variation is variance. and this is the standard deviation squared. We don't use it too much in this class because it's kind of hard to interpret. It can be important in advanced statistics, but not so much for us.